Okay, welcome everyone to my continuation of what is algebra. Today I would like to tell you something about orbits, stabilizers, actions. So groups in the wild, basically. Um, so the whole idea of group theory can be kind of summarized in the following sentence, which is pretty popular. So groups as men will be known by their actions. Maybe a little bit more gender neutral formulated, groups and humans will be known by their actions, right? It kind of makes sense. Groups are abstract objects, but actually in the wild they appear by because they're acting on certain kind of spaces, sets, vector spaces, manifolds, whatever you want. But that's how they usually arise in practice. They arise by acting on something. And I already told you a little bit about that in the video on groups, because groups should be thought of as being symmetry groups of certain objects. Um, and this is kind of what would be called a faithful representation of the group, a faithful action of the group, because all of the group structure is reflected in the geometric object. But you can imagine that you have a huge group acting on a small thing and you kind of lose information. Or you have a huge group acting on a way too big space and the group is still encoded in the space, but there's much more going. And that's kind of what an action in general tries to capture. An action is just you have a group and you operate on something that has a symmetry according to the group. And I will show you an example in a second. So the easiest group I can imagine, which is not completely trivial, is the symmetric group. So the symmetric group is a permutation group, it's a shuffling group. In this picture that I have right in front of you right now, the symmetric group in three letters. And the way I usually like to illustrate it is, so I draw those funny diagrams here. They're called string diagrams. And they work as follows. So I have a symmetric group in three letters. My letters are 1, 2, and 3. And this kind of string diagram illustrates a permutation. So I send 3 all the way to here, I send 1 all the way to here, and I send 2 all the way to here, and then I just count. So I send it 3 to position 1, I send it 1 to position 2, this was supposed to be a 2, and I send 2 to position 3. And you can read off kind of the one-line notation here. So it's a 3 to 1 in one-line notation. But it's really just reshuffling. That's what it is, a permutation group, right? It's just reshuffling the letters 1, 2, 3. And I just like to illustrate it in this funny way. So for example, I could write this one, and my convention is that secretly I have a 1, 2 here, and 2, 1 here. So this is just swapping the two numbers, right? So you have two cards and you just swap them, and I illustrate them with this nice string diagram. And I can imagine the following action of the symmetric group. So symmetric group permutes numbers, but that's just one incarnation of it, right? Why should you permute numbers? You can think of it like, okay, I have green, which corresponds to number 1. I have red, which corresponds to number 2. And I have blue, which corresponds to number 3. And I can think of it as, well, actually, I'm acting with my group on a triangle which has three colored, triangles inside that kind of highlight what angle or what vertex you're looking at. Right, I have a green one. I have a red one here, well, which is right under the red, and I have a blue one here, down here. And I can imagine that it acts on this triangle by just exactly what you think it is. I just decided green is 1, red is 2, blue is 3. So it would permute the triangles, the small triangles, according to that rule. And in the same way, it will change the big triangle, but you don't see that because it's a symmetry group of the big triangle. So I'm using the small triangles to highlight what's going on. And what's happening here? Well, let's see. So 1 goes to position 2. So 1 actually wants to swap with red. And yes, indeed it does. So green goes here, right? It swaps with red. The red one goes to position 3, so it actually wants to swap with blue, and that's what's exactly happening. on the other side, right? So the green one lands here, according to this action. The red one ends down here, and the blue one, of course, then goes to the last spot. And that's how I think of acting on this triangle. I've illustrated this here in steps. So first I swap 2 and 3, which means I swap the colors red and blue, right? That's exactly what you do here. Swaps the colors red and blue. Then I swap the colors, the remaining two colors. Oh, not here. I swap them here, of course. So this is swapping 1 and 2, but as you can see here already in the picture, it's slightly recolored, so you should take the whole picture at once. So now the second strand is actually blue, so I swap blue and green. But that's basically how it works. I will show you more examples in a second, but take your group, and this is an action of the group. And what you can immediately observe here is the following, and that will basically be the definition of an action. So I have a set here, a set X, of those configurations, right? Red, well, let's just do it. Green, my set is green, red, and blue. And I act on it by permuting, and you observe the following. This changes nothing. That's the identity. Okay. And, well, composition behaves nicely. So that's what I explained here. So if I have first this, and then this, then they compose exactly in the way you think they do. And that would be the definition of an action. The definition of an action is exactly modeled by keeping this picture in mind. So the identity object, the identity element should act as an identity, and there should be a compatibility condition between the operation in the group and the operation on the set. That's basically it. It's a very easy idea, very, very powerful. So you will see it in a second. You act on a set, and it's really motivated by this geometric picture, by this combinatoric picture. And the most, at least for this purpose of algebra, the most important invariants, or this most important data you can associate to an action, are the so-called orbits and the stabilizer, respectively, fixed points. Stabilizer and fixed points are kind of the same. I'm going to explain that. So what is an orbit? Well, an orbit is something, you start somewhere, you hop somewhere else, you hop somewhere else, you hop somewhere else. That's an orbit, right? And this is exactly where the name comes from. So in each hopping step, you apply a group element, a GH, I, whatever. And so you start with your favorite element, and you follow it via the action of the group. And that's called an orbit. So let's see that in action. So an orbit is fix an element and follow it, right? Fix an element, follow it. So I fix my element, and I remember that my set here was this one. So my set X is actually green, red, and blue, or green triangle, blue triangle, red triangle. And I just decided that I like the red triangle the most, and I'll follow it through the group action. And what you will see here is that you hit all other triangles, because here are two elements that actually, so the first one, I only care about red. So the first one puts red at the position of green. So I write green into my set. The unit, so the element I haven't even illustrated, this one, of course, just puts red in the set, because so red is, so any element is always in its own orbit, because that's where you start. It's a starting point. And this little thing here down here, it puts red at position blue, so I would write blue. It's kind of I'll show you better examples in a second. This is a reasonably good example. The only thing that is not quite optimal is that my orbit is everything. It doesn't need to be the case. Okay, the orbit can be basically any subset of X. but it's really just an orbit. So you just pick your favorite element and you just follow it through the action. That's what's called an orbit. And well, if you think about following an element, then you can also think about fixing an element, right? In the following way, and it's about stabilizer, respectively fixed points. And the difference between stabilizer and fixed points is whether you want to have an output which is part of G, your group, or whether you want to have an output which is part of X, the space you act on. And it's really just easy. So the stabilizer of my red triangle, for example, are all diagrams, in this case, all group elements, which fix it, which doesn't move it at all. And what could it be? Well, it's exactly those two elements, which I get as follows. I draw my red strand. I know that I get two of them, and it should be fixed. So red should go to red, but it just goes straight. And then I'm free to vary the other two. So I can do, for example, this one. And these are exactly the two elements that I get up here. So, yeah. So stabilizer, fix your favorite element in X and look at all group elements that spits out, that stabilizes it, that spits out the same thing. As illustrated down here. Similarly, there is the fixed points, and that's just pick your favorite group element. So my little g here, and look what it's fixed. And in this case, it's very easy. So green and blue swap. So the only thing that is fixed is red. So you write down red. So it's really looking for fixed points. The difference between the stabilizer and the fixed point set is just whether I want to see what a group element fixes, that's the fixed points, or what is you choose your favorite element of X and you look what stabilizes it. That's the stabilizer. This is a very, 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 very powerful machinery idea. So just you have a group action, and well, fixed points are always interesting. So you just, whether you call them fixed points or stabilizers, doesn't matter. So fixed points are always good, and orbits is kind of the opposite in a way I'm going to explain in a second. Okay, and then you're basically done. You can write down the formal definition. Strictly, there's a left here because the group is standing at the left. There's also a right version, exactly the same, just everything's on the right. Doesn't matter so much. But the action of a group is exactly what you think it is. It's a map. So it acts on X, and now it's just a map which people usually draw by X, G dot X. Just a symbol. It's another element of X. Just a symbol. Okay, and this is my group action. So G acts on every element by a certain operation, and the only thing I would require is that exactly what you have seen from the pictures before. I would require that's the identity, so the trivial element in my group acts as 1, and I would require that, well, you can see it here. The action and the group multiplication are compatible. This is a version of associativity. It's not quite associativity because you always have this chosen X on the right, but it's the version of the right version of associativity in this setup. It's a very easy idea, very, very few datum. And as you can imagine, I mean, there's almost no datum here. So there are zillions of group actions. There are really, really a lot. In practice, you would think of X as not being a set, but maybe it already has some structure, but might be a vector space, for example. And it would require a little bit more. Like if you act on a vector space, the vector space is linear, then you might want your group actions to be linear in a certain sense. If you act on something smooth, then you might want to be your group action to be smooth in a certain sense, and so on. But the underlying definition for a set doesn't have any extra structure, is just this, right? Unitality and compatibility. That's it. And of course, everything I showed you up to this point falls under those two criteria. And then you just write down exactly what I said, the orbit, stabilizer, and fixed point. So the orbit is usually denoted by G times X, following this notation, but now with capital G. So you apply all your small g and just collect what comes up. So here, the stabilizer is These are now all G, which G point X equals X. So everything that stabilizes X, that's a stabilizer. And similarly, the fixed points are all X, which are fixed by your preferred G. So those two are really just the same. The difference is either you want to fix X or you want to fix G, right? So looking for fixed point is always a good idea in any form actually, no, not just in any form of mathematics, but really it's always a good idea. What is fixed is usually an important part of the whole game. And the most important statement you can make about those general group actions are the so-called orbit stabilizer formulas. They come under various names, but I think orbit stabilizer formulas is kind of how to remember them. They involve an orbit and a stabilizer, or a fixed point, which is kind of the same anyway. And they work for a finite group and a finite x as follows. So the orbit times the order of the orbit times the order of the stabilizer is the order of the group. Order of the orbit times the order of the stabilizer is the order of the group. Okay, so let's see. The stabilizer of red is 2, so order is 2. The fixed points of red was 3, order was 3, so order. So 3 times 2 is 6, which is the order of my symmetric group S3. So in case you would not know what the order of S3 is, you would just have computed it. Right? So orbit times stabilizer is the order of the group. And in that sense, in some sense, the orbit is dual to the stabilizer. Orbit is very, very, very nice formula. Orbit times stabilizer is the order of the group. Orbit times stabilizer is the order of the group. And kind of a dual formula or a related formula is that the order of the group times the number of orbits is the sum over all the fixed points. I will show that to you on the next slide, but it's because it's a very useful formula, so don't worry about it right now. So just let me repeat what we've seen so far. Group action, group acts on a set. You write down exactly the conditions you would come up with if you look at these geometric pictures, like groups acting by symmetries on certain objects. So those things here. The most important datum you could associate to such an actions are those fixed points, and dually the stabilizer, and you have those nice orbit fixed point formulas. Okay, let me show you an application why this is interesting, why this is important. This is, of course, a toy model, but it probably illustrates already why those formulas are pretty good and why actions are basically everywhere. So the following problem, a problem from combinatorics. I have a necklace, and the necklace is just a ring, so those things here, with a certain number of points, right? I have a 6 necklace in this case. 6 necklace means really just I have 6 points here, as you can see. Okay. And I don't have just a plain necklace, but I have a 3-colored necklace. And my colors are, as you can see here, green, blue, and red. And that's all conditions I want. So could be any necklace that you can color with 3 colors, basically. So you have completely free to choose the coloring of the vertices. But because it's a necklace, 2 necklaces are the same if you can rotate one into the other, right? So this is a rotation. So I take this point and I pull it to here, and I get this picture, right? For example, this point moves to here, so it moves to here, as you can see, right? 2 necklaces are the same because it's a necklace, right? If I can rotate one into the other. For example, this is not the same here. As you can see, there's no way to rotate this one into this one because the green is missing. Now we can ask the following question. how many ways are there to three colors of necklace? So how many three-colored necklaces are there? And of course, now you might say, okay, I just list all possibilities and try to see those rotational symmetries. So I start with those fixed pictures where I have some ordering, like I fix this one to be the first vertex and so on. And I just look at well, I just count. But it's a really bad idea because those numbers just grow rapidly. They're huge in general. I mean, in this example, you probably still can do it, but they're really huge. There's a much smarter way of doing it. And it works as follows. So I have this necklace, right? My little necklace here. And necklaces are the same if they are the same up to a rotation. So what is really acting here is the rotation group acts on these necklaces by what? By rotation, right? And the rotation group, because I've six necklaces, is given by a 60-degree rotation, by a 120-degree rotation, so by trivial operation, sorry, 60-degree rotation, 120-degree rotation, 180-degree rotation, 240-degree rotation, and one is missing, this 300-degree rotation. So it just has 6 elements. Right? So this is where the 6 comes from. If I would write an n here, I would have n elements in my acting group, and you will also see immediately how to generalize this 3 here. So this is actually a general formula that I'm going to present you, how to color necklaces. And it's just an immediate consequence of what we have seen before. And this is just much better than just writing down all possibilities. But I'm getting ahead of myself. I haven't told you how it works. So this group acts, and it's pretty obvious that it acts, right? And now you would, strictly speaking, you would need to check those axioms here, but it's kind of built that it works. So this rotation group acts. And now we count the number of fixed points. Because I claim that I want to use this formula here. So I should better count the number of fixed points. And what I do is the following. I claim, okay, the unit fixes everything by construction, right? The unit doesn't move anything, right? So it fixes everything. So in this case, I just need to count how many ways are there to color such a pentagon, to color such a hexagon. And there are just 3 colors per vertex, right? So it's 3 to the 6. So there's 3 to the 6 ways, which is a huge number, so you don't want to write down all of them. But I said again, it's pretty easy. That you can choose for each vertex whether you color it green, blue, or red, right? So it's 3, and you have 6 vertices, so it's 3 times 3 times 3 times 3 times 3 times 3, so it's 3 to the 6. Okay, let's have a look at the rotation 180 degrees. That's the next easiest one. So the 180-degree rotation, what it does is it exchanges those points, right? So along the diagonal. In particular, I still have the freedom to choose this one, but then this one needs to go along, right? This one is fixed. If I choose this one, then this one is fixed. If I choose this one, then this one is fixed. In other words, the number of fixed points is 3 cubed instead of 3 to the 6, right? Because along the diagonal, my rotation fixes everything. So I can only choose basically half of the number, half of the vertices. And in a very similar way, you just write down what the fixed points of the other rotations are. It's very easy. You can read it here. I leave it to you to think about it for a second. It's not so hard. It's just much easier than just listing all possibilities. And then you just use a formula. So the sum of all of them divided by the order of the group should be the number of orbits. And the number of orbits is exactly in this case the way how to, I just rewrote the formula, right? So the number of orbits times the order is fixed. So if I want to know the number of orbits, then I divide by the order. So that's what I did here. So here's 1 over g, 1 over g. And these are the fixed points that I just computed. I just add them up, and these are the number of orbits, which is a much faster way of just writing down all 3 to the 6 orbits. And I leave it to you to write down now the general formula if you would replace this one here, let's say by n, and you would replace this one here by m. You certainly don't want to write down n to the m. That's this number here. Then n to the m possibilities and check whether they're rotational invariant or not. This is a much faster way of doing it and a general way of doing it. And although this is just a toy example, I mean, it should be pretty clear by now, or you should have a good feeling now. There are a lot of problems in combinatorics, at least, that you can solve by 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 this formula, or similarly by this formula. I also link you to a nice Wolfram Mathematica demonstration that you can just access. It's linked below, where you can look at a little bit of a very similar problem. It's a 4 necklace, slightly differently formulated, and you study orbits and fixed points of, and stabilizers and fixed points of this 4 necklace. Yeah, but that's basically it for what I wanted to tell you about today. So the point is, groups are really good, of course. There's a study of mathematical study of symmetries, but really groups arise in nature, right? Humans as groups will be known by their actions. So an action is what really makes a group interesting. It acts on a certain object. That means a certain object has a certain symmetry of the group. It doesn't mean it has all the symmetries of the group. The object might be just too small, or the object is too big. It has more symmetries, but at least it has some symmetries encoded in the group. And the crucial things you want to study associated to a group action are these orbits and stabilizers, which give you some nice combinatorial formulas, which are really, really easy to remember. Stabilizer times orbit is group. That was the first one. And the other one is a group times orbits is sum of the fixed points. That's the other one. So they're really, really easy, and they're applicable throughout mathematics, in particular, of course, in this formulation. When I just act on a set without extra structure, then certainly this is something you would see in combinatorics. And my necklace toy model, which I hope you liked, hopefully convinced you that these formulas are pretty useful in practice. Okay, but that's it for today, and I hope to see you next time.